Alright, what's going on everybody? So today we are going to determine the normal stresses in a steel and concrete post. Alright, so we have a concrete post that is 4.5 feet tall with a diameter of 18 inches. So this post also has 6 steel bars through the center of a diameter of 1 1/8 inch. And it's wanting us to find the normal stresses in the steel and in the concrete when a 350 kip axial concentric, so this load P, is applied to the post. All right, so where do we start? Let's find out what information we have. So we know the length of the post, LP, is 4.5 feet. Likewise, LP, length of the post, is equal to the length of the steel. So we know all of those are 4.5 feet. We know diameter of post is 18 inches. And we know the diameter of the steel is 1 1/8 inches. We also have the modulus elasticity of the steel is 29 times 10 to the 6 psi. And the modulus of elasticity of the concrete is 4.2 times 10 to the 6 psi. And we know force P here is going to be 350 kip. So in a previous video, I also mentioned that there is an equation for determining the change in length. And that is delta is equal to P times L over E times A. And we can use this equation to help solve this problem. Because if we rearrange for P, so we know that P will be equal to E times A times change in length, delta, over total length. We know our force P is going to be equal to the pressure or the force that the concrete sees plus the force or pressure that the steel sees. So a combined total of these two forces between the two materials is going to equal our total. And if we insert this equation in for here, we're going to get that equals E of concrete times A of concrete times the change in length of concrete over the length of concrete plus the modulus elasticity of the steel times the area of the steel times change in length of the steel all over the length of the steel. Now the two things we have in common in that are the same are, so the change in length and the total length are both the same. The only things that are different are the modulus elasticities and the areas. So we can factor out this. We can factor change in length over L. So from here we get the modulus elasticity of the concrete times the area of the concrete plus the modulus elasticity of the steel times the area of the steel times change in length over L. So once we have this equation, we can rearrange it to solve strain. So that we get strain, which is this value here, is equal to P over all this. So modulus elasticity of concrete times the area of concrete plus modulus elasticity of steel times area of steel. And I want to put a negative sign here at P because our force is actually in the downward direction. So I'm going to go ahead and put the negative sign for P. All right, so now that we have all this, let's see what information we have that we can put in here. So we have P, we have both modulus of elasticities, and we have both areas. So we have everything here to solve for our strain. So our strain is equal to a negative 350. And we're going to change that to pounds, so times 10 to the third pounds. And we have our modulus of elasticity of concrete, so 4.2 times 10 to the 6 times the area of the concrete. All right, so since we don't have area yet, let's go ahead and figure our area for the steel is 6 times pi fourths times diameter of the steel squared. And the reason we're doing 6 is because we have 6 steel bars that are actually in the concrete. So we have to count for the total sum of the areas. So that's going to be 6 pi over 4 times 1.125 squared. And that gives us 5.9641 inches squared. And for our area for the concrete, we have pi over 4 times the diameter of the concrete squared. And we're going to have to subtract the area of the steel because it is not included. The cross-sectional area of the steel is not included in the concrete. So we have to make sure that we subtract it. And getting all that, we have pi fourths times 18 inches squared minus 5.9641, and our area here is 248.51 inches squared. All right, so now we have our two areas put in here. So this is 248.51 plus modulus elasticity of steel is 29 times 10 to the 6 times our area of the steel, which is 5.9641. Figuring out all this, we get that our strain is negative 2.8767 times 10 to the negative fourth. All right, so we have strain, but we need to find the stress. And with using Hooke's law, so Hooke's law states that stress is equal to modulus elasticity times strain. Now we have both of these, so now we can figure what our stresses are. So our stress in steel is equal to modulus elasticity of steel by our total stress, or by our total strain. And that equals 29 times 10 to the 6, once we plug everything in, multiplied by negative 2.8767 times 10 to the negative 4th. And that gives us a total of negative 8.3424 times 10 to the 3rd psi, or negative 8.34 ksi. And for our concrete, stress concrete sees is our modulus elasticity of concrete by our strain, and that equals 4.2 times 10 to the 6 times negative 2.8767 times 10 to the negative 4th. After we get all our values put in, that gives us 1.20821 times 10 to the 3rd psi, or negative 1.208 ksi. So there you have it. Those are our two answers. That is our normal stresses in the steel and in the concrete when a 350 kip axial load P is applied to the post. Give a thumbs up to help you out. I'll see you on the next one.